Good afternoon. I'd like to thank the organizers for giving me this opportunity and thank you all for tuning in. I hope sometime in the near future I get to see you and meet you all in person. Today I'd like to present some of our results, part of our ongoing research efforts focused on atomic level understanding of the growth and thermal stability of two-dimensional layered materials. In this talk, I will showcase high temperature scanning tunneling microscopy as a powerful tool aimed at developing atomic scale insights into the growth of hexagonal boron nitride layers and their thermal stability on palladium-111. This work is done in collaboration with my friend and colleague, Professor Christian Ciobanu from Colorado School of Mines. And none of this work would have been possible without the assistance and financial support from Dr. Ali Sayer, part of the Air Force Office of Scientific Research. As you are probably well aware, graphene and hexagonal boron nitride are probably the most extensively studied materials belonging to this newly established two-dimensional layered crystals. Over the past 15 years, several novel devices have been demonstrated taking advantage of their unique layer thickness dependent properties. With the realization that the properties and hence device characteristics depend sensitively on the layer crystallinity, layer orientation, and thickness, there has been an increased amount of interest in understanding the growth-related aspects associated with these materials. And understanding and controlling the layer quality will require a fundamental insight into the growth-related aspects. Among these materials, hexagonal boron nitride is commonly grown via chemical vapor deposition using one of the two precursors, ammonia borane, which is a solid, or a borazine, which is a volatile liquid. And the most commonly used substrates are transition metals, which catalyze the decomposition of these precursors. And scanning tunneling microscopy studies over the past decade conducted on these two-dimensional layered crystals, and in particular on hexagonal boron nitride, has shown that the layer quality depends on the type of substrate used. And in case of hexagonal boron nitride, which is lattice matched with nickel 111, one can obtain areas without any corrugations, or on substrates where there is a large mismatch. For example, on palladium or on rhodium 111, one obtains moire patterns. And it has been shown that the corrugations associated with these moire patterns depend on the substrate composition, and one can realize either weak interactions between the substrate and the layer, leading to an atomically flat layer, or a highly corrugated surface if there are strong interactions and a large mismatch with the substrate. For hexagonal boron nitride grown on palladium 111, what we have found is that the surface corrugation depends on the relative orientation of the hexagonal boron nitride on palladium 111. And in our experiments, we found, without any control over the growth parameters, that we obtain a polydomain hexagonal boron nitride, as shown in these scanning tunneling microscopy image here. And these dashed lines show different domains with different moire patterns. And when we measure using scanning tunneling microscopy, the surface corrugation is found to vary with the moire pattern periodicity, which in turn varies with the relative orientation of the hexagonal boron nitride on the surface. It turns out that on palladium 111, hexagonal boron nitride can be weakly or strongly corrugated depending on the domain orientation, and even for the domains with almost the same orientation depending on the extent of bonding. Okay. In this talk, I'll focus specifically on the atomic level understanding, as I mentioned earlier, and therefore I'm going to be focusing mainly on the growth kinetics in the first part of the talk, followed by the studies of thermal stability of the hexagonal boron nitride on palladium-111. And for the first part, where we focus on the growth kinetics of monolayer hexagonal nitride, what we do is we use ultra-high vacuum scanning tunneling microscopy both as the growth tool and as the characterization tool. All our experiments are conducted in situ in the same system. We first grow palladium-111 layers by sputter deposition in a separate system, and we clean it after we bring it into the ultra-high vacuum scanning tunneling microscopy system. And there we expose it to borazine, our precursor, and we collect scanning tunneling microscopy images as a function of deposition pressure, the borazine flux, and the substrate temperature, and the deposition time. And the main findings in our experiments is that we observe very unconventional nucleation and growth kinetics. We observe the hexagonal boron nitride growth at palladium step edges under conditions that lead to higher deposition rates. This is unusual because conventionally, when thin films are grown on epitaxially on a single crystal substrate, when you increase the deposition rate, one would expect to observe islanding rather than deposition at the step edges. And when we increase the temperature, we actually observe hexagonal boron nitride islands on terrace, whereas in conventional thin film nucleation and growth kinetics, one would expect increasing the temperature to result in growth preferentially at the step edges rather than islands. So basically what we observe is somewhat counterintuitive to what is expected for a typical three-dimensional layer growth on a single crystal. Okay, so these are typical scanning tunneling microscopy images that are acquired as a function of deposition time at two different conditions. And what you're watching is time-lapsed images acquired from the same field of view from a bare palladium-111 upon exposure to a low, relatively, what we call as relatively low partial pressure of borazine, and at what we consider as, in this experiment, a high temperature. And what you have observed is, starting with atomically flat terraces, we observe islands formation followed by a complete monolayer growth. Well, I'm going to show you a similar set of images acquired this time at higher pressure than what was used in the previous experiment and at lower temperatures. So basically we are having more deposition flux, and again we start with a bare palladium surface, and these are single atom height steps, and these are single atom high atom islands on clean palladium surface. And watch what happens, and we see complete monolayer coverage after a certain time. And now this is a monolayer boron nitride, hexagonal boron nitride covered palladium-111. And in this case, I will show you in the set of images in the following slide that the deposition occurred preferentially at the step edge. Okay. Based on these time-lapse images, we can now extract quantitative information on the growth mode and the growth kinetics. As a first step, we calculated the coverage of hexagonal boron nitride as a function of deposition time. And I'm going to showcase only these two particular cases because these give the extreme deposition modes. And here in this plot, F, the parameter, the coverage of hexagonal boron nitride on palladium-111. If it's 0, means it's clean palladium. If it's 1, implies you have complete hexagonal boron nitride monolayer formation on palladium-111. And the blue and the red curves here correspond to the two different growth parameters that we have used in this particular set of experiments. And what you notice is that at high pressures and lower temperatures, a complete monolayer coverage is obtained within 245 seconds of deposition, whereas at lower pressure and higher temperature, it takes approximately threefold higher time, meaning that at the higher pressure and lower temperature, the deposition occurs at a faster rate. And let me highlight the differences, the most prominent differences that we observe during these two growth scenarios. When we carry out the depositions at what we call low pressure and high temperature, we observe islands on the terraces before it forms a complete monolayer. In contrast, when we carry out the deposition at higher pressures and lower temperatures compared to the previous run, we observe deposition preferentially at the step edges, both up and down step edges, and eventually we get a complete monolayer. So in both cases, we end up with a complete monolayer of hexagonal boron nitride, but the growth mode is different. I'm going to focus more on these differences in growth modes. And let's consider this one case where the deposition occurs preferentially at the step edges. And I've highlighted here the deposition that occurred at the step edges. And now I'm going to plot the coverage along the steps as a function of time. And so here the coverage at step edges at 0 implies deposition occurred only on terraces. And if the step coverage is 1, that implies the deposition of hexagonal boron nitride occurred primarily at the step edges. And what we notice here is that the time-dependent coverage, that initially the deposition the step coverage seems to saturate with increasing time. Now let's see what happens when we change the deposition conditions. In this case, the step coverage saturates at 0.5, implying there is nearly equal rates of deposition occurring at the step edges and on terraces. Okay. And so as temperature increases, there is a preference for deposition of islands. And now I'm going to focus more on this step behavior and what is unusual in this case. And to get you oriented for what I'm going to be talking about in the next few slides, I'm going to be referring to a step edge in two ways. If the deposition occurs here, I'm going to call it attachment at the down step. And if the deposition occurs here, then I'm going to be referring to that as the deposition at the up step. And as you can see here, there is hexagonal boron nitride attachment at the up steps and at the down steps. Okay. And here on the plot, I hope you can see this. The fractional coverage along the up step is defined as the amount of hexagonal boron nitride that is deposited at the up steps divided by the total amount of hexagonal boron nitride deposited at all the step edges. Okay. And here is a schematic illustration of what we think is happening during this process. That initially, during initial stages of deposition, attachment occurs primarily at the down steps. With increasing time, there is an extension of the already deposited layer towards the up steps. Okay. So without going into additional details, I'm going to summarize what we think is happening. And here is the growth related aspects. So if we consider the rate of borazine deposition, the borazine needs to dissociatively chemisorb on the surface, and this can happen by one or more of the following four aspects. The deposition can occur directly on the terrace, at the up steps, at the down steps, and also at the already deposited hexagonal boron nitride step edges. And each of these arrows is intentionally marked with different lengths that is indicative of what we think are the the increased rates of deposition. So we think the deposition at the down steps is the predominant factor, followed by the deposition at the attachment at the existing hexagonal boron nitride steps, followed by nearly similar rates of deposition at the terraces and at the up steps. So based on this type of rates, we expect that when we introduce high borosine flux and lower temperature, there is deposition of hexagonal boron nitride occurring at the down steps, and these already deposited domains continue to grow both along the down terrace and across the up terrace, leading to a single domain formation along both the terraces. And this is what has been referred to in the community as the carpet-like growth. And if we change the deposition conditions at lower pressures and higher temperatures, we think that the deposition starts at the down steps, but there is additional islands or domains forming on the terraces, which compete with the growth of domains attached at the steps. And I have intentionally colored these differently to indicate that these may be of different domain orientations. And eventually all these domains coalesce, leading to a carpet-like growth. However, the carpet growth mode is different from what is observed here. And under these conditions, one would expect to obtain a polydomain hexagonal boron nitride, in contrast to these deposition conditions where one obtains single domain layer. And we, based on the experimental observations, we propose that the rates of deposition on the steps and on the terraces changes as shown here, and there is a crossover at certain temperature where the deposition rate on the terraces is higher than on the steps. And this leads to the formation of a monolayer via continuous growth across the steps or via preferentially downhill growth. And these are experimentally observed data where in our system we've been able to obtain relatively large single domains at higher fluxes and polydomain hexagonal boron nitride at lower fluxes. So these experimental results are consistent with what we think is happening in our experiments. Okay, so now I'm going to quickly move over to the second aspect, and that is the thermal stability of hexagonal boron nitride monolayer covered palladium-111. And why is this important? As you're probably well aware, the devices based on two-dimensional layers typically take advantage of building vertical stacks of two-dimensional layers where one may have graphene on top of hexagonal boron nitride, or hexagonal boron nitride, graphene, hexagonal boron nitride sandwich structures, or other two-dimensional layered materials supported on other two-dimensional layered materials. If that were the case, ideally one were to deposit and epitaxially grow one two-dimensional layer on top of another two-dimensional layer, then one would have to account for temperature and chemical precursor dependent changes occurring on the existing two-dimensional layer when you're depositing a new layer. And therefore one needs to understand how the existing two-dimensional layer would behave when the temperature is increased. Okay. And so with that in mind, we focused on understanding the thermal stability of a monolayer of hexagonal boron nitride on palladium-111. And what we did is to carry out in situ variable temperature scanning tunneling microscopy studies, and we obtained images while scanning at temperatures up to 1000 Kelvin and using hexagonal boron nitride covered palladium as our surface. And the main findings, interestingly, is that compared to bare palladium, a hexagonal boron nitride covered palladium is thermally more stable And from our studies, what we find is that the stability is increased because the atom mobilities on palladium wrapped under hexagonal boron nitride is significantly suppressed. And without further ado, let me show you what we actually did. And this is an experiment where we are annealing the sample at 1000 Kelvin, and we are maintaining a positive pressure of borazine at this pressures. And this is a time-lapse scanning tunneling microscopy movie or images acquired from the same field of view. And in this particular experiment, we have exposed borazine at this high temperature for doses over 6,000 langmuirs, and we did not observe any deposition of hexagonal boron nitride on these surfaces. And in these movies, you probably have seen some small changes. Let me focus in particular on this thing when we did the same experiment in ultra-high vacuum. And what you're going to be looking at is the changes in the corrugation of this single atom height step and fluctuations in the shape of this vacancy island. These dots that you see is a moire pattern that is developed because this entire surface is covered by a hexagonal boron nitride layer. So this is palladium surface covered with a monolayer of hexagonal boron nitride. And you may also have noticed these slightly different contrast dots, and this is because of it's a domain boundary between these two domains. And again, these are time-lapsed images acquired in the STM while annealing the sample in ultra-high vacuum at 1000 Kelvin. And watch that we do not observe any changes in the moire pattern periodicity, implying that the surface and the hexagonal boron nitride monolayer are intact. If the surface is moving underneath, you would have seen changes in the moire pattern, which we don't. And the other aspects are these fluctuations that you see along the step edges, which is indicative of atom motion along or across the step edges that give rise to these thermal fluctuations. So even though there is a boron nitride layer covering the surface, we do see fluctuations, meaning there is atom motion on the steps under the hexagonal boron nitride. And interestingly, this vacancy island, which is very small, it's about 10 to 20 nanometers in size, the little changes at this high temperature. Now let me come to the other interesting aspects that we observe. I won't go into much of details here, but if you're interested, please send me an email. Depending on the step orientation under the same conditions, and by the way, I should mention that these images are acquired while annealing the sample at 1000 K in ultra-high vacuum, and you can see that this step is highly corrugated, whereas this step is atomically flat, and both these layers are covered by a monolayer of hexagonal boron nitride. And from the analysis of the orientation of these step edges, we know that this particular step orientation is a 2111 type on a face-centered cubic palladium 111 surface, and this we attribute it to the more stable 110 steps. So the steps that are stable have high stiffness, and so there are no fluctuations in this case, compared to a higher energy steps which have low stiffness and they fluctuate more. And this is commonly expected, and that's what we observe even with the hexagonal boron nitride. Another interesting aspect that we observe is these vacancy islands that are in palladium but under the boron nitride layer. As the step edge moves, they detach from the step edges and form their own isolated islands. What we observe when we measure the step heights when it's pinned and when it's detached is that when it's pinned, we measure a step height that corresponds to a monolayer of palladium, implying that the hexagonal boron nitride is taut. It's as if you have a plastic wrapper that is tight across a bowl, and you do not see the actual depth in the surface. Okay? As the vacancy island detaches and the step moves away from the vacancy island, we then measure the step heights that correspond to the vacancy island plus that of the step edge. Okay, so now we can clearly see that we have 2 atom deep hole, a vacancy island on the terrace, and a step edge. Whereas when the island was pinned to the step edge, we only measure the step height as if it's a monoatomic step, meaning that the hexagonal boron nitride is tightly wrapping the vacancy island. And I want to, you have seen this video again, but I want to highlight this in higher magnification. So this is the vacancy island that was being annealed, and this is roughly about 10 nanometers in size. And what you have seen in the time-lapse images is that there are little changes to its size or shape. And this is done over 6,000 seconds, and all we observe is small changes in the shape, and the smaller corrugations in the initial shape of the island, they get a little bit smoothened out. Nevertheless, the island remains the same. And I'll point out to why that is important in a couple of slides. Now, compared to a hexagonal boron nitride covered palladium, if you take bare palladium and if you anneal it in vacuum, this is what we observe. So these are atom islands on a palladium surface, and it's clean, no boron nitride on the surface. As time progresses, these atom islands disappear as part of the ripening process. They lose their atoms to the step edges or to a larger atom islands in the vicinity. And this is a higher magnification image that's obtained from, these are hexagonal boron nitride covered islands, and we observe these atom islands to go away, and this is a higher magnification image showing that the moire pattern remains and these atom islands disappear under the moire. If you take in comparison bare palladium, okay, and we observe both vacancy islands highlighted by these dashed lines and atom islands disappear as time progresses. Okay, no surprise here. But then if we plot the rates of decay of the atom islands and the vacancy islands for bare palladium and hexagonal boron nitride covered palladium, we find that the decay rates are significantly higher when the surface is clean and not covered with hexagonal boron nitride. And in case of vacancy islands, it appears that the vacancy islands are extremely stable on hexagonal boron nitride covered palladium, meaning the hexagonal boron nitride stabilizes the surface. And to explain this, here is a schematic. So for an atom island or for a vacancy island to disappear, there are a few processes involved. One, the atoms have to detach from the existing island, and this requires a barrier, and that is the atom formation energy, and it has to diffuse on the surface. There is a barrier associated with it, the diffusion barrier, and if there is an attachment barrier, then that also plays into the rates of this island decay. And if a vacancy island is supposed to decay, then it requires filling up this vacancy island with atoms jumping across these step edges, which can have an Ehrlich-Schobel barrier associated with this process. And it turns out for bare palladium, you have all these energies and the Ehrlich-Schobel barrier that influence the rates of decay of atom islands and vacancy islands. It turns out that when you have hexagonal boron nitride covered palladium, all these activation barriers are significantly increased. Okay, my time is running. I'm going to quickly summarize. that having hexagonal boron nitride on palladium enhances its thermal stability, and we have quantified the atom and vacancy island decay behaviors. And also, finally, in conclusion, we have identified the growth modes that are associated with the growth of carpet-like hexagonal boron nitride on palladium and the role of deposition parameters. Thank you for your time, and I wish you a happy and pleasant conference.